I'm sure you heard all that, shall I speak loud enough? Meet the hero.
Kia ora tātou, nā mihi nui kia koutou katoa, e nā mana i nā reo rau rangatira mā. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Thank you for the opportunity, and I'm going to talk a little bit about some of my work, but also many other people. And I want to acknowledge Aaron Wall, who is leading a lot of this within my team. So why do we worry about soil carbon? John Sandeman led this work a few years ago and demonstrated that over the 12,000 years we have lost enormous amounts of carbon out of our soils due to intensive cropping and overgrazing. This means that there is an opportunity to put some of that carbon back, and then we also want to find out ways if we can increase the carbon stock of soil. So we're looking at both reducing losses and achieving gains. About 20% of the extra CO2 in the atmosphere has come from these sorts of processes. So this is the approach that we use here in my team, at least, where these are the sites that we've worked over the last decade or so. And it's a carbon balance type approach. So we measure everything going into and out of a farming system, including all of the CO2 exchange. This allows us to look at paddock scale, long-term years worth of data. So I'm going to touch on 4 points of what we've looked at. The first is what is the best supplemental feed, and this is considering both dry matter production and what happens with carbon during the production of that feed. When you put these in, you're often looking either for dry matter for pinch periods or renewing pastures, and as a consequence you have bare soil at either end of that crop. When you've got a bare soil, the microbes continue to consume organic matter in the soil and there is no return from the plants, so you lose carbon during that time period. And I'll just give you an example of how this works and what else then happens. So this is looks like a complicated graph. Time along the bottom here, this is 2 seasons of maize into what was pasture. And this is a carbon balance. So anything below that line is a loss of carbon, and that is a gain of carbon above the line. And there's a lot that happens in here, but basically there is a massive loss of carbon when you harvest the maize. You are taking that carbon that was fixed and removing it from the site. You go through a winter crop and then you go back through maize crop again, and you get another loss. Now what we'd hope then is once it was back into pasture, that carbon would recover through time, according to that green arrow, which is about 1 tonne accumulation per hectare per year. Unfortunately, that did not happen. We do not know exactly why. We think it might be because we had some climatically disadvantageous years, and maybe we just didn't get the inputs that we'd like. But we haven't seen that recovery, and we need that recovery to dictate when we can go back to that land. Otherwise, we're going to get a staircasing downwards of carbon that will actually be quite hard to detect. If we synthesise this, the work that we've done to date on this, on the different supplemental feeds, and we're only just getting going, along the bottom here we have yield, so that's more, and on this axis here we have carbon loss, right? The circles here are pasture pairs, so that's our comparison. And what we see here is that when you get a bigger yield, above ground yield that you harvest, there's a greater carbon loss. And that's because the plants are putting their photosynthesis above ground, not below ground. So you're not getting that return of carbon into the soil. So we need to think about where this trade-off lies, and then this will dictate how frequently we can go back to that land and redo a supplemental feed. These numbers are relatively large. When we scale them up, it might be 1 to 6% net greenhouse gas emissions, and that's just for periodic maize and winter forage. These are estimates. The recovery time of that soil is absolutely key, and getting at that number is challenging. Just by the by, we've also had a bit of a look at some diverse pastures, and they pop up on these green arrows here. There's a lot of different types of diverse pastures, I understand that. All we can say at the moment is that we have no evidence for an increase in carbon stock. Something for further thought. Peatlands, we've heard a little bit about this. both from Jenna yesterday and today as well in Ireland. We have 160,000 drained hectares of peat. They're enormously important for the economy, 1% of the land area that's out there, but there are very large greenhouse gas emissions associated with draining peat. Because they can be metres deep, without change, these emissions will go on for hundreds of years. Just calculating through what this might mean for us, the current methodology in the inventory, you'd end up with just a bit over 4% of net greenhouse gas emissions, but with the updated methodologies that we are moving towards, it will be closer to 10%. We have a limited number of data sets from New Zealand, from work using this eddy balance, carbon balance type work, which would tend to agree with that second bullet point. So the emissions are large and something that we need to consider. So what are we going to do about it? Well, this is a study that was done an international synthesis of the different relationships between water table depth and the size of the emissions. That's the effect of water table there, so that's deep, that's near the surface. And basically what this is showing is that you get large carbon losses that scale more or less linearly with the depth of water table. So if we can bring water table closer to the surface, can we in New Zealand reduce emissions? That's a completely unknown question. Our peats are very different from those in Ireland and other parts of the world. If we do raise water tables, can we put agriculture or production out of that? Is it niche? Is it large scale? Those are really big questions that we need to be considering. And if we can't get good wet agriculture across those, or polluter, do we consider restoration? And how do we do that? That is a very technically, scientifically challenging and enormously important social question as well. This slide, thanks to Mike Beer, on full inversion tillage. This is basically maybe one of the opportunities out there where basically carbon that is in the topsoil is buried lower in the profile, exposing newer soil at the surface, which has the opportunity to gain more carbon through time, while protecting, hopefully, the carbon that we have lower in the profile, and therefore increasing carbon stocks. Mike and his team have observed increased production, reduced N2O emissions, and they have modelled, and this is important and not just something that needs to be noted, modelled pretty impressive carbon sequestration rates. And you can scale that up to the national scale as being interesting and important. One last one then, this is one that might be new to many of you. It is not about soil organic matter, it's called enhanced rock weathering, and we're seeing this around the world as a potential opportunity. This is where natural silicates, so a type of mineral, is ground up and put on the land. And as that material breaks down or weathers through time, it captures chemically CO2. That process is well understood and has been incredibly important in terms of controlling the Earth's atmosphere since the beginning. Can we then harness that ability on farms to sequester CO2? A modelling study, again, of the UK suggested that they could offset about 45% of their greenhouse gas emissions using this approach. This study also is highly dependent on what the actual rates of CO2 uptake are in the real world, not in a lab, not modelled. So Terry Eisen, a colleague of mine at University of Waikato in Tauranga, has field trials established through the Bay of Plenty, one in Waikato as well. And he is hoping, and he rang me just before I missed it, maybe he's got the results now, but it's coming very shortly, he tells me. So there's some optimism there. Okay, to summarise then, clearly it's important to protect the carbon that we have, and then to think about how we might enhance the carbon stocks that we want of the land. And I've presented several, if you like, threats and opportunities. We need to think carefully about how we are growing our feed and whether that ends up with a net negative on our soil carbon stocks. and trade that off against the dry matter we produce and ensure that our recovery periods under pasture, where we rebuild that carbon, are well understood and in some ways implemented by farmers. Maintaining plant cover on the ground is critical, but even more important is ensuring that those plants are investing below ground as well, if you want to maintain soil carbon stocks. Drain peat is something that we haven't done very much on in New Zealand, other than we know that it is an issue and that there might be an opportunity around raising water tables, which will rely on being able to either do wet agriculture of some sense or thinking about restoration to the systems that they used to be. Full inversion tillage and enhanced rock weathering are two approaches that are out there for sequestering carbon in very different ways. They are both reliant on really good measurements of what the rates of carbon accumulation are in the real world. So that's coming from both of those studies, I would hope. I'd like to acknowledge first firstly, the farmers and the land managers that we've had an opportunity to work with, and a long list of people, and they go beyond these people that are here also. Kia ora.